Hello, audience. Welcome to Module 2 to 3 of our centrifugal pump training series. Do like and subscribe this YouTube channel. In this module, we will examine the principal components that make up a centrifugal pump. By the end of this session, you should be able to identify and describe the function of each major part, including the casing, impeller, shaft, bearings, seals, and couplings. This knowledge is foundational for understanding pump operation, maintenance, and troubleshooting in the field. Before we begin examining individual components, let us briefly recap what was covered in the previous module on centrifugal pump principles. You will recall that the two primary components of a volute centrifugal pump are the impeller and the casing, and we also introduced the stationary diffuser ring. In that earlier module, we viewed these components from the perspective of liquid flowing into the eye of the impeller. In today's session, we will take a different approach and examine the pump from a cross-sectional side view. This perspective will allow us to see how all the various components fit together and interact within the pump assembly. Please direct your attention to Figure 1, which presents a cross-sectional view of a horizontal centrifugal pump as seen from the side. This diagram will serve as our primary reference throughout the remainder of this module. Take a moment to familiarize yourselves with the general layout. You can see the casing forming the outer shell, the impeller mounted on the shaft at the center, and the various supporting components arranged around them. We will examine each of these components in detail as we progress through the session. Let us begin with the pump casing. The casing is the visible exterior structure of the pump and serves as the primary containment vessel. Most of the internal components, as well as the liquid being pumped, are enclosed within it. Casings are manufactured from a variety of materials depending on the application. Cast iron and steel are the most common choices, although plastic and other specialized materials may be used in certain circumstances. In oil field applications, as a general guideline, cast iron casings are typically employed for pressures below 1,000 kilopascals, which is approximately 150 pounds per square inch. For higher pressure applications, steel casings are the standard choice. Now, let us turn our attention to the impeller, which is arguably the most critical rotating component of the pump. The impeller is securely attached to the shaft and rotates at the same speed. There are three principal types of impellers, each with numerous design variations. The open type features several blades attached directly to a central hub. The semi-open or semi-closed type incorporates a circular plate called a web on one side of the blades. The enclosed type, also referred to as a closed or shrouded impeller, has plates on both sides of the blades. It is important to understand the performance trade-offs between these types. Closed impellers develop higher pressure, but have a lower flow rate and capacity. Open and semi-open impellers are better suited for pumping slurries, as larger particles can pass through more easily. In most oil field applications, impellers are manufactured from cast iron, though stainless steel, plastic, or other specialized materials may be used for corrosive or chemical service. Figure 2 illustrates the three types of impellers we have just discussed. On the left, you can see the open impeller with its exposed blades. In the center is the semi-open design with the web plate on one side. On the right is the enclosed or shrouded impeller with plates on both sides. Note how each successive design provides greater containment of the liquid flow path. This increased containment is what allows closed impellers to develop higher pressures, but it also means that large solid particles cannot pass through as easily. The shaft is the component that transmits rotational energy from the driver to the impeller. It is typically connected directly to the driver through a coupling arrangement. Shafts are generally manufactured from steel to provide the necessary strength and rigidity. In many installations, the shaft is fitted with a sleeve, which is essentially a hollow cylinder that fits over the shaft. These sleeves are typically made from a hard, wear-resistant material such as tungsten carbide. Their purpose is to protect the shaft from corrosion or erosion in the areas where it is exposed to the seal or packing. The sleeve must rotate with the shaft as a single unit. There are various methods used to secure a sleeve to a shaft, and Figure 3 illustrates one such method using set screws. Continuing with shaft components, Figure 3 also illustrates another important method of securing rotating components to the outside of the shaft, using a device known as a key. In the illustration, you can see how the impeller is secured using this method. A slot called a keyway is machined into the shaft, and a small piece of metal called a key is fitted tightly into this keyway. The impeller hub is machined to slide over both the shaft and the key, creating a positive mechanical connection that prevents relative rotation between the shaft and impeller. Figure 4, which shows this arrangement from the end of the shaft, makes this relationship clearer. Once the impeller has been correctly positioned on the shaft, a nut is used to ensure it remains securely in place. Here we can see both Figure 3 and Figure 4 together. Figure 3 shows the sleeve and key arrangement from a side perspective, while Figure 4 provides an end-on view of the shaft showing how the key fits into the keyway. Notice how the key creates a mechanical interlock between the shaft and the component being secured to it. This is a reliable and widely used method of transmitting torque from the shaft to the impeller while still allowing the impeller to be removed for maintenance when necessary. We now move on to an important protective component, the wear ring. Once a pump is assembled, there is very little clearance between the impeller and the casing. If the impeller were to make contact with the casing during operation, the resulting damage could be extremely costly. Wear rings, sometimes called wearing rings, are designed to minimize such damage. They are fitted to the impeller, the casing, or both, and are made from materials that wear to a smooth surface if contact occurs. Common materials include bronze, which is relatively soft, as well as nylon and cast iron. These materials are chosen because they can be replaced quite easily when they become worn. The location of wear rings within the pump assembly is shown in Figure 5. Figure 5 highlights the position of the wear rings within the pump cross-section. You can see how they are positioned at the interface between the rotating impeller and the stationary casing. Their precise location is critical to pump performance, as they must maintain a very small but consistent clearance to minimize internal recirculation of the pumped liquid whilst preventing metal-to-metal contact between the impeller and casing. Figure 6 provides a more detailed view of the wear rings, particularly on the inlet side of the impeller. This closer view allows us to see how the rings create a controlled clearance between the rotating and stationary components. Pay particular attention to the positioning on the suction side, as we will discuss their additional function at this location on the next slide. Referring back to Figure 6, notice the wear rings on the inlet side of the impeller. At this location, the wear rings perform an additional and very important function beyond simple wear protection. Liquid exiting the impeller rim is at a higher pressure than the liquid at the suction side. Without the wear rings minimizing the clearance at this point, high-pressure liquid from the discharge side would flow back to the lower-pressure suction side. If this recirculation were to occur, liquid would simply circulate within the pump rather than being discharged, which would obviously reduce the pump's output capacity significantly. The wear rings therefore act as a seal to minimize this internal leakage. Let us now discuss pump bearings. Bearings are essential components that serve several critical functions within the pump. First, they support the weight of the shaft and impeller assembly. Second, they ensure smooth shaft rotation. Without proper bearing support, vibration would occur and could cause significant damage to the pump. Third, they prevent lateral movement of the shaft, ensuring that the rotating parts do not come into contact with the pump casing. And fourth, they prevent axial movement of the shaft caused by thrust forces that develop in many types of pumps. There are numerous types of bearings, but one of the most common is the anti-friction or ball bearing. Figures 7 and 8 illustrate this type, while Figure 9 shows a double angular bearing and Figure 10 shows a thrust-type bearing. Let us examine each of these in the following slides. Figure 7 illustrates a standard ball bearing assembly. You can see the inner race, which fits onto the shaft and rotates with it, the outer race, which is held stationary in the bearing housing, and the balls that roll between the two races. This type of bearing primarily supports radial loads, meaning forces that act perpendicular to the shaft axis. The precision ground balls and races ensure extremely low friction during rotation. Figure 8 provides another view of a ball bearing arrangement, showing how it is typically installed within a pump. Note how the bearing is positioned to support the shaft whilst allowing free rotation. Proper installation and alignment of bearings is essential for reliable pump operation and extended service life. Figure 9 depicts a double angular contact bearing. This type of bearing is designed to handle both radial and axial loads simultaneously. The angular contact surfaces of the bearing allow it to support thrust forces in addition to the weight of the rotating assembly. These bearings are particularly useful in pump applications where significant axial forces are generated by the hydraulic action of the impeller. Figure 10 shows a thrust-type bearing. As the name implies, this bearing is specifically designed to handle axial loads, or thrust, along the shaft. In a centrifugal pump, hydraulic forces acting on the impeller can generate substantial axial thrust that must be absorbed by the bearing arrangement. Thrust bearings are positioned to counteract these forces and prevent the shaft from moving axially within the pump. To conclude our discussion of bearings, it is worth noting their physical location and lubrication requirements. In smaller process pumps, bearings may be located inside the pump casing itself. For larger pumps with bigger shafts, bearings are typically housed in separate bearing housings located at one or both ends of the shaft. Because bearings require lubrication to function properly and extend their service life, these housings are often partially filled with oil. A sight glass on the outside of the housing allows operators to verify the oil level without disassembly. Other bearing arrangements may use grease rather than oil for lubrication. Regular monitoring of bearing condition and lubrication is an essential part of pump maintenance. We now arrive at one of the most important aspects of pump design: shaft sealing. Wherever the shaft extends through the pump casing, there is a small gap between the rotating shaft and the stationary casing. Some means must be provided to prevent excessive liquid from escaping through this gap to the atmosphere. In many low-pressure applications, or where pumps handle slurries, pump packing is used as the sealing method. Packing is a soft, flexible, rope-like material that often contains a lubricant. Several rings of this packing material are placed around the shaft in an area known as the stuffing box. A packing gland, secured by gland nuts, is used to gently compress the packing against the shaft, creating a seal. Figure 11 illustrates 5 rings of packing installed on a shaft. Figure 11 shows the arrangement of packing rings around the shaft within the stuffing box. You can see how the individual rings of packing material are stacked around the shaft and how the packing gland at the outer end compresses them. Note also the position of the lantern ring, which we will discuss in more detail shortly. The key point to observe is how the packing creates multiple sealing surfaces along the length of the shaft to progressively reduce leakage. An important characteristic of packing to understand is that, because it does not rotate with the shaft yet remains in constant contact with it, packing generates heat through friction. For this reason, a small amount of leakage along the shaft is actually desirable in most applications, as it serves to cool and lubricate the packing. A component called a lantern ring, also known as a seal cage, serves the same purpose. Figure 12 illustrates the lantern ring. This component ensures that cooling and lubricating liquid reaches the packing, extending its service life and preventing excessive heat buildup. Let us examine the lantern ring in greater detail. The lantern ring has a cross-section similar to the letter H. Liquid is supplied through holes in the ring into the stuffing box, either from the pump itself or from an external source. Referring back to Figure 11, you can see the position of the lantern ring within the packing arrangement. In that particular sketch, the liquid supply comes from the pump's own discharge pressure. In other configurations, the liquid may be supplied from an external source. An additional function of the lantern ring is particularly important when static suction lift conditions exist, as discussed in the earlier module on centrifugal pump principles. In those situations, the liquid in the stuffing box also prevents air from being drawn into the pump along the shaft, which would cause the pump to lose its prime. Mechanical seals represent a more advanced method of minimizing leakage along the shaft. While there are many designs of mechanical seals available, they all operate on the same fundamental principles. The simplest type consists of 2 basic components, as shown in Figure 13. One part, called the head, rotates with the shaft. The other part, called the seat, is held stationary and is secured to the casing. In some seal designs, the positions of the seat and head are reversed. Both the head and seat have highly polished, extremely flat faces that interface with each other. The head incorporates a mechanism, typically springs, that holds the 2 faces in very close proximity to each other. This spring-loaded arrangement is what maintains the seal as the shaft rotates. It is important to understand how mechanical seal faces actually work. Although the faces are extremely smooth, they do not actually touch each other during operation. Direct contact would generate excessive heat from friction. Instead, a very small gap between the two faces allows a minute amount of liquid to separate and cool them. This leakage may be so small that it is measured in drops per hour. Depending on the liquid being pumped, there may be a slight visible leakage outside the seal, or the liquid may vaporize completely, giving the false impression that the seal has eliminated leakage entirely. Mechanical seals offer significant advantages over packing in that they generally require much less maintenance. However, when mechanical seals are used, the pumped liquid must be free of sand, dirt, or other solid particles that could scratch the seal faces and cause excessive leakage. Figure 13 provides a detailed illustration of a basic mechanical seal assembly. You can identify the rotating head, the stationary seat, the spring mechanism that maintains face contact, and the O-rings or secondary seals that prevent leakage around the components themselves. Note how the two polished faces meet at a precise interface. The quality of this interface is critical to seal performance, and even minor damage to either face will result in increased leakage. Figure 14 shows another view of a mechanical seal arrangement, providing additional perspective on how the seal components integrate with the pump shaft and casing. This illustration helps to visualize how the seal assembly fits within the overall pump structure and how the spring mechanism applies the necessary closing force to keep the seal faces in proper alignment during operation. This brings us to an important safety consideration regarding mechanical seals. In applications where liquid hydrocarbons are being pumped, excessive leakage through a pump seal to the atmosphere could create a hazardous situation. One effective safeguard is to install two seals on the pump in a tandem or dual arrangement, with a pressure gauge fitted between them. Under normal operating conditions, the space between the two seals is at a known pressure. If the inner seal begins to leak, the pressure between the two seals will increase, and this change can be observed on the gauge, allowing operators to take corrective action before a dangerous situation develops. In some installations, a pressure switch is provided between the two seals. If the switch detects a pressure increase above a predetermined threshold, it will automatically initiate an alarm and may also cause the pump to shut down. These dual seal arrangements are standard practice in many oil field and petrochemical applications. The final major component we will discuss is the coupling. Couplings are used to connect the pump shaft to the shaft of the driver, which is typically an electric motor. Their purpose is to transmit rotational power from the driver to the pump. Couplings must be robust enough to withstand the shock loads associated with starting and stopping the pump, as well as any changes in pump load during operation. Figure 15 illustrates one common type of coupling. As you can see, the coupling consists of two halves, one fitted to each of the shafts being connected. The two halves engage with each other to transmit torque whilst accommodating minor misalignment between the driver and pump shafts. Figure 15 provides a detailed view of a typical coupling arrangement. Note the two halves of the coupling, each keyed to its respective shaft. The interface between the two halves may incorporate flexible elements such as rubber inserts, gear teeth, or grid springs, depending on the coupling design. These flexible elements serve to absorb shock loads, accommodate minor shaft misalignment, and dampen vibration transmission between the driver and pump. Proper alignment of the coupling during installation is essential for reliable operation and to prevent premature wear of both the coupling and the bearing assemblies. Figure 16 provides an alternative view of a coupling arrangement, further illustrating how the two shaft ends are connected. Proper coupling alignment is one of the most critical aspects of pump installation and maintenance. Misalignment, even by small amounts, can lead to excessive vibration, premature bearing failure, seal damage, and increased energy consumption. In practice, precision alignment tools such as dial indicators or laser alignment systems are used to ensure the driver and pump shafts are properly aligned before the pump is placed into service. This concludes our training module on the parts of a centrifugal pump. We have covered all of the major components, including the casing, impeller, shaft, wear rings, bearings, shaft sealing methods including both packing and mechanical seals, and couplings. Each of these components plays a vital role in the overall operation of the pump, and understanding their functions and interrelationships is essential for effective pump operation, maintenance, and troubleshooting. Thank you for your attention and your valuable input throughout this session. Do like and subscribe this chemical process engineering channel created by Mr. Rahul Srivastava, who has 23+ years of work experience in hydrocarbons processing projects and a chartered chemical engineer by qualification for more such process engineering videos. Also, do comment on which topics you want the future videos on this channel. Thanks again for watching.